Welcome to the explainer. So picture this. You're sitting in the exam hall. The clock is ticking down. You can practically hear the tension-building music in your head. You open up your Cambridge physics past paper. Maybe it's syllabus code 0625, 0651, 0652, 5054, or even 9702. And boom, the practical exam is staring right back at you. Well, today we're focusing on a concept I absolutely love. I call it the Master Chef, Physics Cambridge Exam Strategy. Think of it like a recipe for absolute success. Your raw data, those are your ingredients. Your calculations and processing, that's the cooking phase. And your final conclusions and evaluations, that is the beautiful plating. Now let me introduce you to two students we see literally every single year. First, there's Alex. Alex is the kind of student who overloads his answers with raw physics facts, dumping every equation he knows onto the page, but completely forgets to actually analyze the data sitting right in front of him. Then we have Sam. Sam rushes through the paper, completely missing the crucial command word requirements, and ends up measuring the wrong variables entirely. If we looked at their papers side by side right now, you'd see an absolute sea of red pen marks. But today, we're going to transform those red marks into green check marks. We are demystifying the core competencies you need to completely ace these practical exams so you don't fall into the same traps as Alex and Sam.
Okay, let's dive into this. The official Cambridge framework is the actual benchmark for scientific inquiry and practical skills. We're not just pulling strategies out of thin air today. We are extracting the fundamental skills straight from the Cambridge curriculum past papers. You see, when examiners sit down to grade your paper, they've got a highly specific rubric. They aren't just looking to see if you know what a voltmeter does. They want to see if you can act like a real, accomplished scientist. Can you record observations systematically? Can you interpret data accurately? Can you evaluate your own experimental method? These are the real ingredients of our recipe today. If you want to become the master chef of your physics exam, you really have to understand the kitchen you're cooking in, and this framework is our kitchen.
So here's our roadmap for the explainer today. We'll be looking at 4 universal skills. 1, the foundation, which is your setup and readings. 2, the analysis, focusing on processing data. 3, the evaluation, looking at flaws and fixes. And finally 4, the master plan, for designing investigations. All right, starting off with part 1, the foundation, setup, and readings. Let's transition right into our first core skill, setting up the experiment correctly and taking accurate initial measurements. This is exactly where our friend Sam usually loses marks right out of the gate, just by rushing. The foundation is all about decoding the command words and setting up your apparatus with absolute precision. Because think about it. You can't cook a great meal with spoiled ingredients, right? And you definitely can't write a perfect conclusion with flawed initial readings. A perfect example, straight from a past paper, involves determining the spring constant of a spring. The very first instruction is often to measure L0, which is the unstretched length of the coiled part of the spring before any load is applied. Identifying your base variables is step 1. Now, Alex might just grab a ruler and measure the whole spring, including the little loops at the ends. But the instructions specify the coiled part. Precision really matters. To get this measurement accurately from a ruler that's clamped vertically, you can't just eyeball it. You actually have to use a set square, aligned with the bench, to take the reading directly straight across from the spring to the ruler. That is the level of evidence gathering the examiners require.
And this level of precise setup applies across literally every single physics topic. Take the focal length experiment with lenses, for instance. You've got an illuminated object, a lens, and a screen. The distance between the object and the lens is u, and the distance from the lens to the focused image on the screen is v. Now, if the examiner tells you to set u to exactly 20.0 centimeters, you have to ensure your ruler is perfectly parallel to the bench and you are looking straight down at the markings to avoid parallax error. This is a massive recurring theme. Whether you're measuring unstretched springs, positioning lenses, or reading a thermometer, identifying and accurately recording these initial variables before the true experiment even begins is the absolute foundation of your success. And remember, you must explicitly state these precautions in your answers to secure those method marks.
Moving right along to part 2, the analysis, processing data. Okay, let's move to the next crucial phase. What exactly to do once you actually have your raw data? You've gathered your ingredients, now it's time to cook. This is where we bring in the analysis, and honestly, this is where Alex usually struggles. Alex will write a whole beautifully written paragraph about the theory of heat transfer, but the question just asks to process the data in the table. We need to apply a structured framework here, kind of like the Peel framework you might use in essay writing. Point, evidence, explanation, link. You make a point about the trend, provide evidence from your readings, explain the calculation, and link it back to the physics principle. And here's something absolutely critical. Examiners are incredibly strict about table formatting. Just look at this data from a thermal cooling experiment, comparing 2 beakers. Notice the column headings? Examiners expect tables to be perfectly formatted with the correct units incorporated directly into the headings, separated by a forward slash. So it's T/S for time in seconds and theta/degree C for temperature in Celsius. Do not, I repeat, do not write the units inside the actual data cells, next to the numbers. It clutters the data and it can actually lose you marks. Your raw readings here, the changing temperatures over 30-second intervals, are your raw ingredients. We're going to use these to calculate average cooling rates in just a moment.
Let's look at another classic analysis technique, finding patterns. Often, raw readings alone just don't reveal the physics secret. You have to derive new values. Take an experiment testing the resistance of a wire at different lengths. You measure the length L and the potential difference V. The raw numbers might look like a totally random jumble, but the command word will ask you to calculate V divided by L for each length. When you do this derived calculation, you might find that the result is approximately constant. And boom, that derived value is your cooked dish. It proves the proportional relationship. When you're asked to justify your conclusion, you must reference these derived values explicitly. You'd say something like, V/L is approximately constant, ranging only from 0.041 to 0.043, which is within the limits of experimental accuracy.
And of course, the ultimate data processing tool is the graph. Let's quickly walk through the required steps using a balancing meter rule experiment. You're measuring distances A and B from the pivot to balance a load. Step 1. Always plot your independent variable on the x-axis and your dependent on the y-axis, making sure to label them with units like A centimeter. Step 2. Pay close attention to the prompt. Often it explicitly says you do not need to begin your axes at the origin, 0, 0. Doing so when you don't need to will just cramp your data into a tiny corner, losing you scale marks. Step 3. Draw a smooth, thin best fit curve or a ruler straight line of best fit, ensuring you have an even distribution of points above and below the line. Step 4. Calculate the gradient G by choosing 2 points on the line that are far apart. In this specific experiment, finding that gradient G actually allows you to calculate the weight of the ruler using the formula W equals G times P. Pretty neat, right? All right, part 3, the evaluation, flaws, and fixes. Let's shift our focus to the evaluation stage. We've gathered data, we've plotted graphs. Now we must think critically, exactly like an examiner, to spot errors and suggest improvements. This is plating the dish, making sure it's absolutely perfect before we serve it. Let's do a quick mental challenge. Imagine a complex data table showing cooling rates of water. Can you extract the core trend and find the flaw in how the experiment was run? Here's the challenge. We have an experiment comparing the rate of cooling of hot water in beaker A, which has insulation, versus beaker B, which only has a lid. A student from another school wants to replicate your results. Is it important for them to make their initial starting temperature exactly the same as yours? Think about the physics at play here. Heat transfer depends on the temperature difference between the object and its surroundings. I'll give you a second to think about the flaw in starting at different temperatures. Got it? If you said yes, it is absolutely critical, you hit the nail right on the head. If the starting temperatures differ, the average cooling rates are heavily affected by the environment, completely skewing the conclusion. For example, if beaker A starts at 85 degrees and beaker B starts at 70 degrees, beaker A is initially going to cool much faster simply because there's a much larger temperature difference between it and the room temperature. To truly test the effectiveness of the insulation versus the lid, the initial thermal conditions must be identical. When writing your perfect peel paragraph here, your point is that starting temps must be equal. Your evidence is the formula for average cooling rate comparing the temperature drop over time. Your explanation is that heat loss rate depends on the temperature gradient with the room. Therefore, your link is that differing start temperatures completely invalidate the comparison of the materials. And this brilliantly illustrates how stating sensible precautions and consistently controlling environmental variables is what secures those tricky evaluation marks across all the physics topics. Let's recap some gold standard precautions. If you're doing an electricity experiment with a resistance wire, you must switch off the circuit between readings. Why? To keep the wire at room temperature, because a hotter wire has a higher resistance, which totally ruins your variable control. If you're doing a cooling experiment, keep away from open windows to control drafts and room temperature. If you're doing optics with a refractive index block, place your pins as far apart as possible to reduce angular uncertainty. Memorize these fixes, guys. They are your secret spices to sprinkle on literally any evaluation question. And finally, part 4, the master plan, designing investigations. Now, let's transition to the final boss of the practical paper, designing a full experiment from scratch. This is our final system, the ultimate test of your MasterChef abilities. You are given a blank page and a list of apparatus. It's time to build the menu. 7. That is the magic number. I really want to emphasize the weight of this massive 7-mark investigation question. It sits at the end of the paper and it terrifies a lot of students. Alex usually writes a scattered essay, and Sam usually forgets to draw a table. But a structured approach, our physics success blueprint, is the key to capturing every single one of these 7 points. This isn't about creative writing. It's literally about ticking boxes on the examiner's secret checklist. Let's break down the ultimate 5-step checklist required for any 7-mark planning question. You need to memorize this sequence. Step 1, explain the setup and the method briefly. What are you connecting to what? Step 2, state the key variables you will keep constant. Control variables are easy marks. Step 3, identify the independent variable. What are you deliberately changing? Step 4, draw a blank table with correct column headings and units. Step 5, explain exactly how you will use the readings to reach a conclusion, usually by comparing data or plotting a specific graph. If you follow this matrix, managing your time carefully, you absolutely guarantee top marks. Let's see how it applies.
Let's apply this to a real past paper scenario. The question asks, does the type of container affect the time taken for water to be heated from room temperature to boiling point? You have a copper can, an aluminum can, a glass beaker, and a Bunsen burner. Step 1, setup. Pour water into a container, place it on the tripod over the Bunsen burner, insert a thermometer, and start the stopwatch. Step 2, constants. We must use the same volume of water, the same initial temperature of water, and keep the Bunsen flame intensity identical. Step 3, change. We will repeat the experiment, changing only the type of container, copper, then aluminum, then glass. Do you see how structured that is? We are systematically isolating the variables.
So the crucial point is step 4, the table. I cannot stress this enough. Remind yourself that drawing the empty table with precise units is often the easiest mark on the paper, yet it's the one so many students forget under pressure. For this experiment, your perfect table heading would have a column for type of container, with rows for copper, aluminum, and glass, and a second column titled time to boil/seconds, or T/S. Then for step 5, the conclusion. You simply state that you would compare the times. The container with the shortest time to reach 100 degrees Celsius is the best thermal conductor. And just like that, Master Chef status achieved. I want to wrap up with a provocative thought that challenges you. Look at this scenario from a past paper. You are handed a flexible track, metal balls of different masses, a tape measure, and a stopwatch. Could you confidently apply our 5-step framework right now to investigate the time taken for the metal balls to stop moving? What exactly would you change? What would you keep constant? What would your table look like? Apply this structured skill set to your next past paper question and watch your grades soar. Thanks for joining me on this explainer, and I'll catch you next time.